Histograms are simply a way of visually representing what we previously talked about, frequency distributions. So as an example of a histogram, which is a graph consisting of bars of equal width drawn adjacent to each other, where the height of each bar represents a frequency from a frequency distribution, we have this as a first example. So we're looking at the heights of black cherry trees, probably in some orchard. So the height is represented down here on the x-axis, or on the horizontal axis, and the frequency is on the y, or the vertical axis. So if we want to know how many trees had a height between 60 and 65 feet, we would simply look at the height of this bar, and that tells us we had 3 trees that had a height between 60 and 65. There were also exactly 3 trees that had a height between 65 and 70. There were 8 trees that had a height between 70 and 75. Looks like 10 trees had a height between 75 and 80, etc. So you can imagine, or try to imagine, the frequency distribution that would go along with this. In the class between 60 and 65, you would have the number 3. In the class between 65 and 70, you would have 3. And in the class between 70 and 75, you would have an 8. Here's a larger histogram. This one is slightly skewed, and we'll talk about skewness in a moment. But this is slightly skewed. I would not say that this represents a normal frequency distribution because it's not symmetric. But again, this is simply a histogram that would represent some frequency distribution. In the previous section, we talked about frequency distributions, and we also talked about relative frequency distributions that dealt with percentages. If we took both of those and created histograms from them, we'd have a histogram and a relative frequency histogram. It turns out that those histograms would have the exact same shape. So instead of the y-axis having the frequency, if we had the y-axis represent the relative frequency, or that percentage, these would have the same shape. Normal distributions have histograms that are bell-shaped. So again, you're going to start low, just like with frequency distributions. You would start low, you'd get higher to a point, and then you'd drop off again. And they'd be roughly symmetric. So visually, this one looks like it probably could be considered normal because it starts low, gets to a peak, and then drops to low again, and it's roughly symmetric. It may be fairly rough, but it is roughly symmetric. A uniform distribution histogram have bars that are all approximately the same height. So, in other words, you should be able to draw a straight line across the top, and most of the heights of the bars will be about that. So this one is a fairly rough approximation to a uniform distribution, but I would say that this is probably fairly uniform. So consider the difference, or the similarities rather, between a frequency distribution that we have on the left and a histogram that we have on the right. So again, just to drive this home, if our class was between 20 and 24, and we had 3 of our data in that class, then our bar between 20 and 24 would go up to 3. Similarly, our bar between 25 and 29 down here would go up to 5, etc., etc., etc. So this histogram represents the same exact data as this frequency distribution. If we wanted to know how many data points were in the original data, we simply need to add up the heights of all the bars in our histogram. This is the same idea as adding up all the frequencies in a frequency distribution. So if I wanted to know how many data were in the original data set, I could take 3 plus 5 plus 8 plus 13 plus 14 plus 12 plus 11 plus 7 plus 5 plus 2, add all those up, and I would have the amount of data, or the number of data that were in the original